Let's talk about one of the most basic questions ever. Why does stuff move? And maybe even more puzzling, why does it stop? You push a toy car, it rolls for a bit, and then it just grinds to a halt. It seems so simple, right? But the real story behind motion, well, that's a mystery that took humanity centuries to solve. So let's unravel it together.
I mean, really think about it. You give a ball a good roll across a field. It goes, it slows down, and then it stops. The most obvious, common sense answer is that it just ran out of its go. Like the push you gave it just kind of fizzled out. And you know what? For a really, really long time, that's exactly what everyone, including the smartest people around, believed.
For centuries, this was the accepted wisdom. The idea was that every object has a natural state, and that state is just sitting still. Rest. It makes a lot of sense, right? I mean, everything we see around us eventually stops moving unless we keep pushing or pulling it. It took a few truly brilliant minds to come along and say, hang on, what if we're looking at this whole thing completely backwards? And this guy, Galileo Galilei, was one of the key players. He, and later the legendary Isaac Newton, looked at these same everyday things and came up with a totally revolutionary idea. They suggested that maybe things don't just run out of steam. Maybe there's something else happening, some kind of invisible influence, a hidden actor that's actually causing things to stop. And that hidden actor has a name, force. Honestly, if you can wrap your head around this one concept, you've pretty much unlocked the secret to all of motion. So, let's break it down. What exactly is a force? At its heart, a force is just a push or a pull. Simple as that. You push a shopping cart, you pull a door open, a bat hits a baseball. All of those are forces. But check out the key part of that definition. A force can change an object's motion. It doesn't mean it always does. And that little distinction, well, that changes everything. This right here is the absolute core of the whole idea. For an object's motion to change, to speed up, slow down, or turn, it has to be pushed or pulled by an unbalanced force. If all the forces acting on something are perfectly balanced, completely canceling each other out, then its motion just isn't going to change, period. It'll just keep on doing what it was already doing. Okay, picture this. You're trying to shove a super heavy refrigerator. You push on it, but it just won't budge. Why not? You're applying a force. Well, it's because the force of friction between the fridge and the floor is pushing back on you with the exact same strength. The forces are balanced. Nothing happens. But then you get a running start and give it a massive shove. Now your push is way stronger than the friction, the forces are unbalanced, and boom, the fridge finally moves. So let's bring it all the way back to our rolling ball. It doesn't just run out of motion on its own. It's being actively stopped by an unbalanced force. And that hidden actor we were talking about? It's friction. The rubbing of the ball against the grass, the air pushing back against it, that's the unbalanced force that slows it down and brings it to a stop. Mystery solved. So this whole new understanding that you need an unbalanced force to change motion is what allowed Isaac Newton to lay down his 3 world-changing laws of motion. And that brings us right to the first one, which you might know as the law of inertia. It builds directly on everything we've just talked about. This is the genius thought experiment that changes the game. If friction is what stops the ball, what would happen if you could just snap your fingers and make friction disappear? What if there were no unbalanced forces at all? What would happen to that rolling ball then?
And here's Newton's answer. It sounds a little formal, I know, but it is absolutely profound. What it's saying is that an object just sitting there will stay sitting there forever, and an object that's moving will keep moving at the exact same speed, in the exact same direction, forever, unless some unbalanced force messes with it. That stubborn tendency of an object to just keep doing what it's doing, that's inertia.
Now, here is a really important point. Inertia is not a force. It's not a thing that's pushing or pulling. It's just a fundamental property of matter. It's this built-in laziness, this resistance to having its motion changed. Things don't naturally want to stop. They naturally want to keep going. They resist change. And you feel this literally all the time. You're on a bus and the driver slams on the brakes. What happens? Your whole body lurches forward. That's your inertia in action. Your body wants to keep moving at the same speed the bus was. Or when the bus takes off suddenly, you get thrown back in your seat. That's your body resisting the change from being at rest. It's all inertia. So, what decides how much inertia something has? It's simple. It's mass. The more mass an object has, the more inertia it has.
Think about it. It's way easier to get an empty cardboard box moving than one that's packed with heavy books, right? That's because the box of books has more mass and therefore more inertia, more resistance to any change in its motion.
Okay, so Newton's first law covers the no change scenario. But what about when forces are unbalanced? What happens then? How much exactly does the motion change? Well, for that, we need Newton's amazing second law, which is basically the official rulebook for acceleration.
Now, real quick before we dive into the second law, we need one more little concept. It's called momentum. You can just think of momentum as mass in motion, or how much oomph an object has. A huge truck moving slowly can have the same momentum as a tiny superfast bullet. It's a combo of how much stuff is moving and how fast it's going.
So this is how Newton first wrote his second law. It's a bit of a mouthful, but what he realized is that forces don't just cause motion. They change an object's momentum. The bigger the unbalanced force you apply, the faster you change that momentum. And this whole idea can be simplified down into one of the most beautiful, powerful equations in all of physics.
F equals ma, force equals mass times acceleration. This little powerhouse of an equation explains everything from why a baseball curves to how planets stay in orbit. It gives you the exact mathematical relationship between force, mass, and the change in motion we call acceleration. It's the code.
So let's see this in action. A baseball is flying at you, it's got a ton of momentum. To stop it, to bring its momentum down to zero, your hands have to apply a force. Now, if you're a rookie and you just hold your hands out stiff, the ball stops almost instantly. That's a very fast change in momentum, which means you feel a huge force. Ouch. But if you're a pro, you pull your hands back as you catch the ball. You increase the time it takes to stop it. And by increasing the time, you dramatically reduce the force you feel. It's just smart physics. So you see, this isn't just a bunch of abstract stuff for a science test. Understanding force, inertia, and acceleration gives you a completely new way to see the world. It reveals the hidden rules behind pretty much everything you do, from driving your car to playing catch.
So let's boil this all down. What are the absolute key takeaways? First, objects don't want to stop. They want to keep doing whatever they're doing. Second, that resistance to change is called inertia. Third, the only thing that can cause a change in motion is an unbalanced force, like friction. And finally, F equals ma is the rulebook that tells us exactly how that change is going to happen. When you really get these laws, it's like you've learned the fundamental grammar of our physical reality. You can suddenly read the story of why things move the way they do, and you can even predict what's going to happen next. It's just that powerful.
But notice I said they describe almost everything we can see and touch. Newton's laws are perfect for our everyday world of cars and planets. But what happens when you start moving close to the speed of light? Or when you shrink down to the quantum world of atoms? Well, that's where the rules start to bend, and a whole new, mind-blowing chapter of physics begins. But that's a story for another time.